Excellent. Hi, everyone, and welcome again to another Learn Live session. My name is Glenn Stevens. I'm here with my good friend and colleague, Jason DeBoever. Hi, Jason.
Hey, Glenn. Good to see you again.
Yeah, likewise. We've got an exciting session today. We're nearly at the 2/3 mark of this series on machine learning. Today's session, create and understand classification models in machine learning, is going to be a little bit of a departure from what we've done so far, but also a little bit of the same. It's going to be some good, exciting fun. Now, for those of you who are just joining in, because we do get a lot of repeat visitors, we also get some people who are just checking stuff out, or maybe they're interested in a particular topic and they're watching this later. Do you want to introduce yourself to the world?
Yeah, hi, I'm Jason DeBoever. I'm a senior product manager at Microsoft, and I'm focusing on AI and ML content for our docs.microsoft.com, our Learn, Azure Architecture Center, things like that. So basically the places you go to learn about stuff Microsoft.
Excellent. Cool. And I didn't introduce myself before, but my name is Glenn Stevens. I'm a senior content developer here at Microsoft, working mostly on Learn Live. I like the sessions here. Excellent.
Awesome.
So let's have a look at where we are in the journey so far. So we're in that second one. It looks like there's only 5, but there's actually been like 5 already that we've done. And we're at this session here, create and understand classification models in machine learning.
Yeah, 6 of 9 we're at. So we've already put away 5 episodes over these last 6 weeks or so.
Excellent. And we've got a little bit to go as well. So we'll be looking at further things like confusion matrices. We're looking at architectures and hyperparameters and optimizing model performance. So a lot of interesting work still yet to come. And today's one should be fun. In fact, let's bring up the module link. So if you're following along, and we actually encourage people to look at the content as we go through it, and also follow on and do the module in your own time as well. Sometimes you just want to sit and absorb the content and then go back to it. We're really covering the Learn content from the existing Learn module. So if you're following along, just watching us, you can go back to the Learn module and do that in your own time as well. But the link is aka.ms/learnml-classification.
Yeah,
and in fact, go ahead, Jason.
I was just going to point out, the way we're doing things here with the Jupyter notebooks that are built right into our Learn interface. We mentioned it the first few episodes, but I think it's time to revisit, making sure everybody remembers, or everybody who's now watching is aware. You can jump right into the web browser, execute all the code. We've provided the basic code for you that we're going to be demoing. It's right there. But this is a full execution environment. Change the code, tweak the code, figure things out by making changes. This is the best environment for learning. It's fantastic. Just go in there, run code, change code, run it again, fix the errors, run it again.
For sure. Excellent. Cool. You know what? We've got some people in the chat already saying, hi, Jason, hi, Glenn. It's my pleasure to keep going with you. Excellent. Some good return
wonderful.
visitors.
Thank you for coming back. So happy to have you.
Love it. All right. And what are our learning objectives for today's session, Jason?
So today we're going to learn about classification models, how they differ from our regression models that we've actually been working on for most of our episodes so far. We're going to build models that will do the classification, and we'll learn how to improve them, how to judge them. In other words, how to run through tests, see how well they're doing, and improve them during the training process as well.
Awesome. Now we are live and interactive. We've already seen that nice, lovely comment coming through as well. We're always interested to know where people are coming from as well. If you've got some general questions as we're going through the session, we'll try and get to the answers of those in appropriate time. Sometimes that's around about the exercise time. We want to make sure we don't lose the flow too much of the session, but we're very mindful of the people who are here live wanting to interact. So keep some questions coming through, and we're looking forward to it. And you know what? Some of the questions will be answered not by us, by our excellent moderation team. And Jason, you're good friends with some of them, or these are your colleagues as well, maybe both.
These folks are fantastic. That's right. So they are definitely capable of answering all your machine learning questions. I do hope they throw some of those questions our way, because it's fun to answer them in the session as well. But yes, these folks are amazing experts, all Microsoft folks who work in this day in, day out. So yep, they'll be fielding some of your questions and then passing some of your questions forward on to us.
Excellent. Cool.
All
Well,
right.
let's get into the session. So let's have a look at the overview of what we're doing. I'm going to pass that over to you, Jason.
Yeah, on to me. So classification models. Very, very simply, what's a classification model? Especially, how does it differ from the regression models we've done so far? Well, simply put, a classification model is going to predict what class or what category something belongs to. So we might have categories like red, green, blue. We might have categories like fruit, vegetable. We might have categories like vehicle or airplane. I suppose an airplane might be a vehicle. Let's say automobile or vehicle. Mobile or plane, you know what I'm getting at. So categories like that versus our standard regression models, which are trying to find continuously variable values such as height, weight, things like that, that you might have a continuous variation on rather than a fixed bucket like a category. We have a scenario that we're going to be working with as we talk about this, and it seems it involves snow and slopes again, just like a lot of our scenarios. You want to tell us a little bit more about it, Glenn?
Yeah, sure thing. Well, this one's kind of nice. It's we're working with a charity that is really responsible for looking at things like snowfields, where people are maybe skiing or hiking, etc. And we're looking for essentially the chance of an avalanche, and we're trying to use machine learning to predict that. So we're going to use some classification models for that. That's our aim for today. We'll look at the features that we have. We'll try and build a model that works with one and more of the features. So as we'll go through the exercise, we'll do it incrementally so you can see how we can apply that process and try and measure our models as well to make sure that we're getting the most accurate one that we possibly can. And preventing avalanches is a really good business case. We certainly don't want lots of tourists on days where there's likely to be a massive avalanche, and we want to protect the public safety of people.
I certainly don't want to be hosting a bunch of tourists that end up buried under snow. So I would agree with you there.
Yeah.
Shall we move on?
Let's.
All right. I already mentioned briefly what classification models are. Here we see the example of apple, banana, cherry. So maybe we're showing pictures and saying, is this an apple? Is this a banana? And categories, really, you can think of it just as things where one isn't greater than the other. So we're not looking for one to be larger or more than another. An apple is not inherently more than a banana, nor is a banana inherently more than an apple. They're just different. So that's how we can think of our classification models versus, of course, regression, where we're trying to detect things that are either more or less than another thing. Today, we're going to be focused on a particular type of classification model called logistic regression. And logistic regression is a type of binary classification model. And Glenn, what do I mean when I say a binary classification model?
Now, obviously, that's going to be true or false. That's what I'm expecting, right?
Well, it certainly can be.
Yeah. So it's kind of got it's probably a prediction model, right?
Yeah,
Well,
anything that's kind of, like you said, true or false, or kind of up or down, or two things, basically, right? Binary, it's going to be two things, and true or false is absolutely the most common of our binary prediction models, or our binary classification models. In fact, a lot of the terminology around our binary classification models kind of assumes that we're talking true and false.
So you're talking really two-state.
Exactly. It's a two-state. Yes, absolutely. So logistic regression is a great one to start with if we're coming from a discussion about regression models. And actually, that's a little interesting, isn't it? Because I talk about regression models, and when I say regression model as a group of models, I'm very specifically referring to those things where I can predict more or less of something, right? The height, the weight, where one prediction is inherently more or less than another versus categories, right? But yet, when I say classification is a different category of models, a different type of models, but one of them is called logistic regression and has regression in the name, well, that's confusing, isn't it? It's another one of those jargon warnings.
It is, but I can see on the chart on the screen, it actually looks like a regression as well. we've got our red line that's looking like the linear regression, but our logistic regression is in the blue. So it's probably doing the same thing, but it's a different shape, almost like the polynomials we were talking about before, right?
Kind of, yeah, and it definitely starts with that same idea of regression, where we have, in fact, mx plus b, that taking your intercept, which would be your b, your slope, which would be your m, and your x is your input variable. Taking that function like we did for linear regression, slope, intercept, and input variable, is still what we're going to be doing with logistic regression. However, there's a few more steps. In order to turn it into a yes or no, true or false type category, we need to be able to convert the values to a 0 or 1. And we'll have 1 be true most of the time, but it really could be anything. 0 be false most of the time, but really it could be anything. So we want to be able to do that conversion. And for that, we use something called a sigmoid function or a logistic function, hence the name logistic regression. It acts sort of like a regression function, but then we take that mx plus b formula that we're going to train, and it's always being run during the process through that sigmoid function, which I've actually expanded out right here for you. And you can see it is not going to be as intuitive.
Yeah, well, I mean, when we were going through the exercises during our rehearsals, for example, when we look at that formula, it's kind of like that's actually pretty complicated. And it's also, we don't really need it when we're doing the exercises either. Most of the frameworks that we're using hide that aspect for us, but it's really a matter of knowing when do we apply logistic regression.
Yeah, we're not going to be thinking about the natural logarithm or Euler's number here, which is what that E represents, or any of these kind of weird things like that. We're not going to be thinking about those during the process, but I wanted to kind of get it there because as Glenn and I were talking, it became obvious that we came from linear regression, and there was a real intuition about where that slope and intercept went in the graph. And we've lost that now. We don't have that intuition because that formula does kind of throw it all off. So we're going to see an intercept and we're going to see a slope, but they're not actually directly real world analogs anymore because the function we're passing it into throws it off. So before we move on, let's talk a little bit more about that function curve. What it does is make sure that our values are all between 0 and 1, absolutely no matter what m or x or b are. So if this formula, if our slope and our intercept and our input variable combine to be 1 million, then that is getting closer and closer to 1, but never achieving 1. So as I go 8, 9, 10, it's close. If I go to 1 million, it's going to be a lot closer. If I go to 10 million, it's going to be 10 times closer to 1, but it's still not going to be 1. It'll never actually achieve 1. And the same thing on the 0th side. So what this means is, as we're training, our training loop can be raising up those parameters, m and b, higher and higher and higher as it's more and more sure that it's 1, without us ever worrying that it's going to essentially overflow. It's never going to go past 1 into a zone that's meaningless for our binary classifier. So it's just helping it be more and more sure about that classification.
Excellent.
And you can see that it's getting us along a kind of probability scale here. So that X feature was input, and our output then, if we input 6 based on whatever we had as our parameters here that produce this graph, we input 6, we're going to get an output of somewhere around 0.75, it looks like. Now that gives us that probability. 0.75 is neither 1 nor 0. And in fact, we know we can't actually get a 1 because we only get closer and closer to 1, closer and closer to 0. But we can pick a point. What's the most obvious point, do you think, Glenn?
Well, the halfway mark really between 0 and 1.
The halfway mark is definitely the obvious point, like the point where we would do a normal rounding. So at 0.5, we're going to either go up or down. So 0.51, we're going to call that a 1 prediction. And at 0.49, we're going to call it a 0 prediction. That's only the most obvious choice. There are good reasons that you might make other choices of threshold, including just noticing that the predictions work better, that your actual true falses work better by picking a different threshold. It could be that simple, but there are other reasons that you might as well. But for sure, the obvious answer, 0.5, or the midpoint there, is the most common as well as the most obvious.
Cool. Now, we actually have a question that's come in. Why do we call logistic regression, why do we call it logistic regression instead of logistic classification?
Yeah, I mean, at the end of the day, it's because of historical reasons. So it uses the idea of regression as the input, and then it runs it through the logistic function. So, but before it's literally a regression before going through the logistic function, and after going through the logistic function and picking our 0.5 threshold or whatever other threshold we pick, at that point it becomes a classification. But yeah, it's confusing. So it would be great if we didn't have that confusion and have to explain that every time we brought up logistic regression. But there you have it. It's for historical reasons is the short answer.
Awesome. And thanks for the question. Keep them going.
Yeah, fantastic.
Right. All right. So we've got our demo to run into. So in this one, we're going to look at the Avalanche data, and we're going to take some time essentially visualizing it, looking at where the trends are. No different to what we've done with other forms of regression as well. We'll look at the data, we'll do a simple logistic regression model, and then start playing with it and applying some of the thresholds there. So let me share my screen. And
while you do that, I'm going to look at this other question we've got. Is this S-shaped curve a representation of a single independent variable? Of course, that's what makes it, it's easiest to view kind of a single input and a single output when we do it that way. But it's really a question of the response on the Y. So what that means is it's really a question. It's a function of the result, no matter how many input variables you have. Because if you had a traditional regression, you'd have a line or a plane or a hyperplane that you would use mapping your input variables. But either way, we have a result function for that output curve. What we're doing with the S shape, it's a visualization, but what it really means is simply as the mx plus b or m1x1, if we had multiple features, plus m2x2, et cetera, plus a final b, right? If we had multiple features, all of that, whatever number that results in, and again, it could be 1 million or 2 million or 10 million, ultimately, we're taking that high end, so anything basically above 1 is getting, and even approaching 1 is getting squashed down so that it's flattened. So the S is a visualization, and yes, it's easiest to visualize with only a single independent variable, but regardless, you're always going to take the single output variable and squash it down to 1, which we could always come up with some way to visualize as an S-curve.
Awesome. Thanks, Jason. Well, let's jump over to the exercise. Hopefully everyone can see my screen all right. And if you're following along, there's the Azure Sandbox for Learn. You should be able to activate that and run the exercise. We're using Jupyter notebooks here, which is a wonderful little tool that allows us to execute some Python code as we're executing it. So in our case here, we're going to look at that Avalanche data. So our first cell that we're running, it's going to import a library here, the stats model, and also pandas. We're going to essentially get access to the graphing library. We will be visualizing a lot of this data, and then we've got a CSV file that we're loading in as well. So we'll load in that into a pandas data set and then have a quick look at the data set just to see the columns that are there and get a sense of the data that we're working with. Always a good idea. All right, it's taking a little bit of time. It normally takes about 10 seconds or so, I think, for this one. Yeah, it looks like the data's loaded here. And we've got some interesting columns here. We've got the avalanche, which is really predicting, or the outcome of, it's not really predicting, but it's stating the outcome of this particular row's details. 0 obviously means no avalanche. 1 means there was an avalanche. There's the number of visitors. This column here represents the frost level on that particular day. We've got the thickness of the snow, the wind, the number of weak layers, which are like the layers of snow that we have, and tracked out, which means really whether or not that particular
Whether
those
people were
paths,
hiking on it, I think.
yeah, essentially, and
there is
lots of footprints.
There's a glossary. Oh, maybe we don't have the glossary on this one. I think
No,
maybe
the glossary is on the third exercise when we actually start adding in multiple features. So we're starting simple with just one feature in this first exercise. But yeah, we'll see the glossary a little bit later. But we will actually have a look at the data and the columns. So we're going to do the box and whisker charts just to get a sense of where the trends are. So if I execute that, we'll be able to see it visually. You'll get a better sense. So we're mapping out the various columns, like the frost level, the thickness, the number of weak layers, and the number of visitors, to see where it has an impact on the avalanche. So if I look at this here, we've got the frost level. So 0 means there was no avalanche on these entries, and 1 means there was an avalanche. So if I look at the frost levels, it looks like the higher frost levels increases the chance of an avalanche. That's what I'm taking from this. And if I scroll down again and look at something like the fresh thickness, we could actually look at that and go, there's not much difference between these two entries for no avalanche and an avalanche on that day. And as we scroll down the columns, again, we can see the weak layers. So the number of weak layers, which I think the weak layers is like the strength between the layers of snow. Now, if you think about it, you go, well, if there's not much strength between the layers of the snow, it sounds like that's probably more of a chance of an avalanche. And if we look at the data here, that tends to support that quick hypothesis I just made in the last 30 seconds. But you can see where the trends are lying, right? And as
turns
Jason,
out neither Glenn nor I are snow experts or experts in the domain of snow and avalanches, unfortunately. But
yeah.
which goes to the point we've made before about you should really know your data before actually doing analysis on it. But demos and all.
Yeah. But you always say this, and it's very true, is that you should be working with a domain expert, ideally, with this data. I mean, I go snowboarding once a year, and I've read Smiller's Feeling for Snow, and that's the only expertise I have.
I've read Jack London's Call of the Wild, so that.
There you go. All right, and if we look at the number of visitors, we can see there's a slight difference, but there's not much impact or change with the likelihood of an avalanche. So we can see some of those trends that are happening. But we're going to start very simple with today's model and just look at some of the details. We'll start with the weak layers as we go forward. But our simple logistic regression model is actually not that complex. And when we're doing the ordinary least squares, like in the first few exercises, it's a very similar process. But we also want to make sure that we're testing our model as we go. So we're going to do that process where we split our data set into our training data set and our validation data set. And this is the process here. We're going to get that data set. We'll specify the test size as 0.3. So our training data set will be 70%, and our test size will be 30% of that data set. So I'll go ahead and execute that, and it'll just tell me the number of rows that I have. So 766 for training, 329 for validation. Excellent. So now we actually go and create the logistical regression. And if you look at the code, and if you're coming back from several weeks of following us, that you'll actually see the code is not too different. In fact, we've got our stats model that we're importing, but our method for doing the training is not OLS for ordinary least squares. It's logit. And Jason and I pronounce this very different. So how do you pronounce it, Jason?
I pronounce it logit, which is it's technically a different function from the logistic function. It's for our purposes, it's the same. For any mathematicians out there may be going, that's not exactly the same thing, but for our purposes, it is. But I pronounce it logit, but I'll be honest with you, I don't actually know for sure that that's correct.
Yeah, Logit. That's the way I type it essentially. But what we're doing here is we're looking at the weak layers. The weak layers are the input, and we're trying to predict the avalanche. And we're passing in the train. So that's the training data set that we're using, and we're calling fit. So the fit method is the actual one that trains the model. And then after this chunk of code executes, we'll just print out the fact that the model's been trained.
We actually have a couple questions here. I'll jump on real quick while you execute. Oh, wow, that was fast, but I'll still answer the question. So is logistic regression considered a linear method? The basic answer is no. The curve itself is a non-linearity. The actual function affects creating, you can't create a plane with it, and therefore it's not a linear method. And the next question is, why use a sigmoid function, aka the logistic function? Can we use other functions for the curve? So the logistic function works perfectly for what we want to do, which is get between 0 and 1. So it's ideally suited to that. However, you can certainly do regressions with other curves. They're just going to have dramatically other features. So, I mean, really what it comes down to is if you can get a derivative for the loss function, then you can train it and you can improve that function as long as it's something that you can get a derivative for. Then you can train that function. However, the sigmoid function is optimally shaped for our two-class classification, getting us from 0 and 1, between 0 and 1.
Excellent. Well, you're getting all the good questions today, Jason. That's fun. All right. So the next thing we want to do is print out the model summary. I'm actually going to get rid of this print statement. It doesn't actually format it as nice. And I'll print out the summary, and then we can see that the details of the logistical regression. So we can see things like the number of observations. A lot of this is statistical information you may not use. We'll be using some of this a little bit later. We've also got our intercept and our weak layers. So the weak layers has a positive impact on the scoring. So that scoring will be put into that formula that you showed earlier. So if you're thinking, well, is that going to create the same line like a linear regression? It won't. It'll be put into that other formula that Jason was showing before. But we can see weak layers certainly has an influence on the likelihood of an avalanche.
Yeah, given the logistic regression function, aka sigmoid function that we're using with our intercept and with our coefficient or our slope for our weak layers there, you're not going to actually see those numbers exactly on the graph like we could with that linear regression. However, we can see, for instance, that intercept is going to be below 0. It's going to be transformed, but it's going to be below 0. And the weak layers, we can tell we're going to have an upward slope. So as our weak layers go up, we can tell at least that our output variable is going to go up. We don't know exactly how and in what shape because we're not that good at intuiting the sigmoid function, but but we can at least tell that much, that they're going to go up together.
Awesome. All right, so let's actually use our model. So once we've got our model trained, we'll actually use it to predict some samples. In this case here, we're going to take the first 4 entries, I think, from the test data set that we have, and we'll look at the weak layers, and then we'll use that to essentially predict it and then see what comes out. So it'll look at a number of entries. So there's a weak layer value of 5, 4, 7, and 0. And we can see that when we've got the different weak layers, it's predicting the chance of an avalanche. So it's not actually doing the classification of you will or you won't. It's saying this is what we think the probability will be. So in this case, 5 yields a 56% chance, 4 yields a 50% chance, 7 a 67% chance, and 0 a 29% chance. And you can see that relationship. So as the weak layer value increases, there's a higher chance of an avalanche. So that's that.
And the perhaps secret here too is you can see right now, despite that we're trying to ultimately get to classification, at this step we actually are doing a regression. We are getting a continuously scalar value, which is the probability of each class. So that's another way to look at why it's still called a regression, is because right now we are getting that continuously variable value of a probability.
Cool. All right, so let's move on, and we'll actually have a look at a chart to see how this is executing. So we've got the data for weak layers, and as the weak layers go from 0 upwards, we can see that there's a trend. So as the more and more weak layers you have, the more and more chances you have of an avalanche. So obviously, if you had a day above 20, you're probably pretty guaranteed to have an avalanche, just on that factor alone. But the chart also goes below 0 as well, which is interesting. So we're not going to have a negative 10 weak layers. But why would that be there?
Well, for one thing, it's a symmetrical shape. So understand that one of the things we do have a limitation with regard to the sigmoid function is it's symmetrical. So essentially, we trained from 0 to 40. Let's just say, I don't actually know what the range of but from 0 to 40, we trained that shape. And since we're fitting a sigmoid function, by definition, because it's symmetrical, we're going to get that shape of a tail. So that's why it does go below, to -10 and -20. We're never going to actually see those values. But as low as we can go, we do still have a 30% or so chance of avalanche. So we don't actually want this to bottom out at 0, 0. We want to demonstrate that even with no weak layers, we still have a 30% chance.
Yeah. It's interesting, isn't it? So let's actually print out some of the values. You're talking before about 0 to 40. Let's have a look at our data set and see what our weak layers are. And in this case here, the minimum number of weak layers we have is 0, and the maximum number of weak layers in our data set is 10. But it's doing the predictions there. One of the things about logistical regression is what it kind of implies what you see. It actually reasonably predicts well outside of its range.
Yeah, so when we have our linear regression, of course, if we, let's say we had an unusual number of weak layers, we ran into a situation where we had an unusual number of weak layers that was twice as much as we'd ever seen before, and we were trying to predict. Well, let's say we were doing linear regression, but we were using it to predict a likelihood. Well, if we went outside all the data we'd ever seen before, we might predict a likelihood of 200% with a linear regression, because linear regression is just, if you try to go beyond your data set, if you try to extrapolate, it's just going to keep doing more of whatever that trend line is. The nice thing about logistic regression is, if 10 layers is the most you've ever seen and it's likely to cause an avalanche, it's actually pretty reasonable to say that 20 is probably more likely to cause an avalanche. And all we're going to do with that logistic curve is get even closer to 1, which is exactly right. So the extrapolation actually does work. Even we still recommend trying to only predict on data that you've actually seen, just as a general rule. But this actually works a lot better with extrapolation, because you're never going to get extreme output values. You're still always going to be between 0 and 1.
Yeah. Cool. All right, well, let's look at our last few steps here in the exercise. We want to actually look at the average rate of avalanches for particular values. So, for example, where there's 0 layers or weak layers, and also where there's 10 weak layers. If you go ahead and execute that, we can actually see the average rate for avalanches for 0 weak layers is 0.38. And likewise for 10, it's 0.77. And that's really just having a look at some of the averages over the entire data set, I believe. No, over the training data set. So we can see that information there. Now, the other aspect, I'll go ahead, Jason.
Really, to drive home what you just said, that we're not looking at the output of a model right there, right? We're just looking at what does our real data tell us, so that we can kind of compare this, right?
Exactly. Cool. So next we'll actually jump into the classification step, where we'll actually define that threshold, and we'll use that same threshold that we were talking about before, which is the halfway point between 0 and 1, 0.5. And then essentially we'll look at that and apply the threshold. And then when we see that the values that are over 0.5 it's presenting it as a percentage here, we'll actually specify that the classification is true. As in, we predict there's going to be an avalanche on that day. And likewise, when it drops below 50%, we'll classify that it's false, and there's a likelihood that it won't be an avalanche. But in this case here, we can see that the value points 0, 7, 4, and 5. So all of these percentages for 5, 4, and 7 are over 50%. So its classification is true. Likewise, when it's 0, its classification is less than 50%. So its classification is false. And that 0.5 threshold is just an arbitrary value that we've chosen because it's a nice middle point. But there might be times that you actually choose a different value for that point as well. I think you were speaking to that before, Jason.
Yeah, and there are, while I'm talking, do you want to actually change that value and just run it again and show the folks?
Oh, yeah.
0.6 or something. But yeah, there are analysis techniques we can do when we're reviewing our model and checking the performance of our model, where we're going to actually look at the curve and see how it's performing, and then select our threshold or our cutoff for classification based on what the actual outputs are. So we don't have to retrain our model if everything's being categorized the right way, in the right direction, yeses and nos. It's just the threshold that needs to change. We don't need to retrain. We can just do a little bit of analysis and find out what the optimal threshold is. And we'll actually be talking about that in later episodes.
Right. Awesome. So I changed it to 0.65, and you can see that it changed the classification. So 3 of the entries are now false and 1 is true. So I'll change it back because it's probably likely going to influence the other cells that we have in the notebook. All right, so let's have a look at the performance on the test data set. So this is applying what we've got the training and seeing how well it predicts the values from the data that we've extracted from that original data set. So we'll essentially use the prediction value if it's going to be greater than the threshold, and then we'll look at essentially the average number of predictions that turn out to be true based on the model over the entire test data set, and then see what it comes out with. So in this case, the model's correctly predicting an avalanche or no avalanche 65% of the time, which is not too bad. It's better than flipping a coin. But as you'll see over the next few exercises, we can actually improve on that score as well. So that's a look at our first exercise, just doing the very simple logistic regression and then working through it. And Jason, I'll get you to take the screen back.
All right, on it.
Awesome.
So let's talk a little bit more about how we get our classification models to be sort of optimized, if you will. One thing we haven't done is talk about how training happens with our classification model. So once we actually build the model or decide what our model or our model architecture is going to be, in this case, that's the logistic regression model architecture, the training gets us to some optimal set of parameters, right? If we're only using the one feature, then the parameters in question are a single weight and bias, or kind of the M and the B of the MX plus B. But of course, that expands out when we have lots more features. But how do we get to those optimal parameters? Well, the training process is the same as it was with linear regression, but the cost function is not the same. So remember, with linear regression, we have a slope, and if we imagine just one feature, so we're kind of picturing it that way, we have only the one feature, then with that slope, we're going to say, all right, what's the distance between a real world data point and what my slope says it imagines or predicts the data point should be, the output should be. And we just kind of total up and average all of those differences, and that's our loss or our error. That's how we do it with the linear regression. Right, so far so good, Glenn?
Yeah, I think so. But mentally, I'm thinking about the linear regression and the mean squared error, and it seems like the way that the slopes are defined, you would probably not want to use the mean squared error for logistical regression.
Exactly. So with logistic regression, the thing is, towards the extremes, we're kind of collapsing the possible space that we have. Or a simpler way to put it is, instead of having this whole world of numbers where my M and my X and my B could all total 10 million or 12 million or 30 million. And so my error might be 30 million because my M and my X were just way too large. So my error is super large. That's never actually going to happen with this curve. No matter what my M and my X and my B are, I'm never going to have a giant error. My error is always going to be between 0 and 1. Worse, it's not actually going to be consistent. So as we get towards the extremes, it's going to actually taper off. The amount of error is going to taper off so that a value here doesn't seem that much worse than a value here, even if it was supposed to be a 1. It was supposed to be a 1. If you got here or here, then it doesn't seem that much worse, but it is. It's a lot worse. It's like a third worse according to the curve. And so what we want to do is have an error function that's going to kind of inverse that flattening. And that's what this error function does. So you can see that what I actually have is the loss here. So this is mapping if I was supposed to be a 0 and I predicted a 1, or if I was supposed to be a 1 and I predicted a 0, what's the actual loss going to be? And so you can see as we're much farther away, we're punishing it much more. And what that does is actually flip, because remember that ultimately we want a 0 or a 1. So if we're much farther away, we're by definition of this curve, if we're much farther away, we're in the point where it's flattening the slope into almost nothing, right? Applying this curve reverses that. And so we're going to say, oh, well, if we were wrong by a whole 1, in other words, it was meant to be 0 and we picked it 1, or it was meant to be 1 and we picked 0. So we're off by a whole 1, which is the maximum possible. We're at near infinity. Just like the sigmoid function is at kind of the inverse of basically 1 over infinity at that point, when it's completely flat. So this is reversing that. So you can almost imagine it as just turning it for loss calculation purposes, using this. So basically mean squared error plus this basically almost stretches that out. It very nearly kind of stretches that function out for the purpose of calculating loss. It's pretty cool. It's a little hard to wrap your head around, but you don't really need to. It's just important to kind of generally get where this is coming from. You don't need to fully absorb all those concepts, which it's really hard to do. It's really hard to do without just like sitting down with a lot of equations and just going, okay, I see. Okay, I see.
But it looks like it mirrors the equation that we have. Like when we look at linear regression, it looks like the mean squared error, which is really a distance calculation, it would fit. And it's almost like we've got this exponential nature or the limited nature where it approaches 0 or 1. The log loss, it actually mirrors that distance calculation, but it's dealing with exponentiality.
Yeah, exactly. I mean, it's definitely using the same idea. It's using the same measurements. It's just then running it through the exponential function. It's just running it through that in order to make the extreme values more extreme is kind of really what it comes down to, because with the sigmoid, the extreme values actually are not sufficiently extreme. Cool. We've got another demo coming up. Glenn, do you want to run us through that?
Yeah, I do. It's a shorter demo here, really. But what we're going to do is we're actually going to take a look at the log loss function against that Avalanche data set again. We'll look at how we can calculate the accuracy of it, and then essentially look at some other things like how can we detect what that accuracy issue actually implies. I won't give it away too much at the end. But let me just change the screen over here. And just a reminder, if you've got some questions, it's always good to send them through as well.
Yes, indeed.
It looks a little empty at the moment. All right. So we've got our logistical regression model. This is going to start very similar to what we had before, where we're bringing in the CSV file for the Avalanche, and we're looking at the head, basically the first 5 rows of that, and then we'll also do a box and whisker chart on the Avalanche. So the Avalanche across the x-axis and the weak layers across the y-axis. So again, it'll probably take about 10 seconds to execute this. Well, 6 seconds. It's nice and efficient today. Now, so we can see the data set. I'll just scroll up. So we've got our Avalanche, number of visitors, frost level, thickness, wind, the number of weak layers, and whether it's been tracked out. But we're still working with that one parameter at the moment, which is weak layers. So, and we can see the same chart from before, where we have the number of weak layers is a good predictor, I would say, based on this data set, of the likelihood of an avalanche. So we're going to go through the data set, and the next step is we're going to split our data set again into the training data set and also the validation data set. We're using a different percentage this time, but we're taking 75% for the training and 25% for the validation set. So I'll just run that cell. That will do the split, let us know how many records we've got. Now, the next thing we're going to do is essentially do the training. So we're doing this as the baseline going forward. We'll do a logistic regression on this formula. So weak layers as the input, trying to predict avalanche against the training data set. Oops, and then we'll call the fit method that actually does the training, and we'll output that we've done the training. And then after that, we'll do the summary. This is no different to what we did essentially in the first exercise, but we're seeing the number of observations, the intercept, and the weak layers. You might go, well, there's a different correlation here and a different intercept. And the reason for that is that we actually have different data from the first exercise because we have a slightly larger data set fit in the training data. But essentially, we're running through the same steps. So we can see that we've got our intercept, our weak layer. There's definitely a positive correlation between the weak layers and the likelihood of an avalanche. Now, there's also the p-value. We'll look at the p-value in a little bit more detail in exercise 3. But the p-value essentially lets us know if that is going to be likely to be statistically significant. We'll talk about that more a little bit later. With machine learning, we try to avoid most of the statistical stuff because there's other mechanisms around it. But we'll get back to that later. Jason, you might want to speak to that. I'm not sure.
Yeah, we'll wait till later, like you said.
We'll wait till later. All right, good.
Yeah, we've got a really nice time to bring it up in exercise 3, so I just figured I'd wait till then.
Okay, nice. All right, but as we do, we're going to assess this model visually because it's one of those things people have. I always find this fascinating that people have a lot of their memory system linked to the visual parts of their brain. So when we see things visually, it's actually easier to process. But if we look at this, it's kind of an interesting thing. We've got dots along the top, we've got dots along the bottom, and what kind of appears to be a straight line, but I don't feel like it's a straight line. I was telling you.
There's even kind of something, even if it was a straight line, it's sort of something we need to talk about here, which is why does it slope at all? Because it looks like we just have data points everywhere.
Yeah, and this is an interesting one because it also lets us know something else. Like if I hover over these dots, these are really data entry points from our data set saying that there's data points where there's 0 weak layers and an avalanche happened, 1 weak layer and an avalanche happened, and so on, all the way to 10. And likewise down the bottom. So where there's 0 weak layers, there's days where there's no avalanche, and there's entries for all of them. So we can say that the weak layers, yeah, there's data entry points there. Maybe we should have had a chart that shows the size of the circle indicating like the number of entries for that as well to give a better sense of the data.
And yeah, exactly. I was going to say, yeah, if these bubbles were bigger, you'd see that the top right, we have big bubbles to show that there were a lot of examples.
Yeah.
And then the bottom left, you'd see that there were big bubbles to show that there were a lot of examples. Whereas right now, the way we have this chart, unfortunately, just says there's at least one example at every combination, which isn't super helpful. It's not helpful at all, quite frankly.
No. But sometimes just to look at the data and analyze it, it's very helpful in that aspect. You go, okay, there's some information there. You might affect the chart. But if we zoom out, because you look at that, you go, it's very close to a straight line. But you know that feeling you have in the back of the head where you go, something's not right. Like I had that with this chart the first time I saw it.
Or maybe it makes you feel dizzy because you look at it and you think it's supposed to be a straight line, but you're feeling all wobbly.
Yeah, well, no, not to that extent, no. But if we step back,
just me.
Yeah, if we step back, we actually see that it's not really a straight line; it's a curve. But we actually don't see the outsides of that range. That's our range of our data set, 0 weak layers to 10. But the way we've got the intercept and the coefficient for the weak layers calculated, the prediction curve line, kind of we are along that straight path there. And we can see that, yeah, it's really the curve that's scoping, predicting the outcome of an avalanche. Anything to add there, Jason?
No, I mean, it's like you said. I mean, we'd obviously love to have those bubbles bigger again so we could see why it's predicting that curve. That would help a lot. But the reality is we see that if we had weak layers of, say, 7, we can see exactly where that would intercept the trend line, which is somewhere around 0.7, 0.7 likelihood of an avalanche. And we would predict that to be a yes avalanche because we're still assuming 0.5 is our cutoff. So.
All right. Awesome. So let's actually use that and start applying the log loss function that we were talking about previously. So we've got our predictions where we're going to test against the data set, and then we're going to test against the avalanche and correlate that to the predictions and see essentially what our log loss function is. So in this case here, we've got a log loss of 68.68. So it's a little bit like mean squared error when we were looking at before. A higher number means a larger error. So that number, you want it as small as possible when you're testing your model, essentially.
Yep, exactly.
So we also want to predict the accuracy. So we want to look at the proportion of predictions the model got correct. And later we'll also do some summarization of that to look at where there's things like false positives and false negatives. So here we've got some predictions. We're running through it. We've got our avalanche prediction. This is really our classification. That's where the prediction is greater than 0.5. And then we'll look at those entries directly. So we've got our predictions, which are 0.78, 0.68, and 0.56. Now, all those classifications, because they're over our prediction layer, 0.5, they're going to be true, true, and true. So maybe if we had a different prediction layer, we changed that in the notebook, ran that again, we could see that like there's not a likelihood of an avalanche on that last entry. I'll just quickly change that back. But once we've got that, essentially that prediction process, we can apply that again against the whole data set. And we're getting the accuracy of roughly around 61, 62%. So it's helpful to know that. But Jason, I'm not sure if you're talking about the false positives and false negatives, because those are two different things as well. So, for example, you gave a great medical example when we were talking, I think yesterday.
We have slides coming up for this.
Oh, we do? Oh, wonderful. Yeah. All right. Maybe that's what I'm referring to. But we want to look at the false.
We also do have it in the code block here, yes.
We do. So we want to look at the ones where we predicted an avalanche, but an avalanche didn't occur. And likewise, where we predicted an avalanche wouldn't occur, but we had one. So obviously, those two outcomes have very different meanings for the forestry's department. So if we don't predict no avalanche and an avalanche happens, obviously that's a bad thing. If we predict an avalanche and no avalanche happens, that's not so bad because we told people not to come to the park on that day.
Yeah, so exactly. It's not necessarily even always about being as right as possible. Sometimes it's about being as safe as possible, or as conservative with your safety guidelines as possible. So exactly what you said. I'd rather be wrong, but tell people to stay off the mountain.
Yeah, Exactly. The very different outcomes. So here we've got wrongly predicted an avalanche 21% of the time and failed to predict the avalanche 17% of the time. So that's obviously the one we'd be more concerned with, the failure to predict. But it gives an idea about how we can analyze the data, how we can classify, use the log loss function, and also see where we get those false positives and false negatives. A very nice look at how we can analyze the data a bit further. And we'll come back to some of the analysis and measurement in our third and final exercise. But we'll send it back to you, Jason.
Super duper. All right.
Oh, we do have a question in the chat though.
Oh, so we do.
Yeah. Can logistic regression work with high dimensional data set in general?
So there's nothing that would stop it. In fact, because logistic regression is so inexpensive to execute, like linear regression, it's a very inexpensive machine learning model that actually in some ways makes it very desirable for high dimensional data. That said, let's bear in mind that if you have very high dimensional data, you may also require a complex function to fit it. You may not, but it's something to bear in mind. I mean, you start talking about very high dimensional data, I start wondering if we're talking about things that are on the order of like doing image recognition, where I'm dealing with thousands and thousands of features, or even tens of thousands of features, or things like that, and NL, natural language processing. Of course, those are much more suited to neural networks. So the answer is there's nothing stopping logistic regression from working with data sets with a lot of features, except the complexity of the function. So if it'll work, it'll work. There's nothing stopping it. In fact, it's again the cost of execution of the model is very low, which makes it desirable in cases where you can get a acceptable accuracy or acceptable performance. Cool. So let's talk about how we can improve things. And one of the obvious ways to improve a model is to give it more data. That could be more records, but obviously it could also be more features. We could predict on more things than just weak layers, for instance. So predicting based on more features is going to just give us a richer set of information to model. So that is something that we will often try to do, is get as much information about each record as we can. Of course, as long as it's accurate and all that good stuff. Another thing we can do is try to find if there are correlations. Actually, remember, just in response to that last question, we talked about the complexity of the data or the complexity of the model. And much like when we did polynomial regression, where we decided to kind of hand increase the complexity, we could do that with logistic regression too. We could use polynomials. I could take one of the features and square it or cube it. However, we can also do something else here. Glenn, thoughts on that?
Well, yeah, it's interesting. I was looking at the composite features, and my mind went, well, what if we had data that had like the number of people who are yodeling on the mountain and versus the number of visitors? Like, is there a composite to that? Would that affect the avalanche? I mean, we don't have that data, but when you combine two factors, that actually might be a direct input. That's what you're referring to?
Yeah, we don't have that data, but I'm very curious to see if yodeling really can cause an avalanche, because we can break glasses that way, shatter glasses that way. Now I want to know. Now you've made me curious. So that may actually that may actually be something that's important. Not just the yodeling by itself, but maybe yodeling is grouped with, I don't know, low barometric pressure or something, because of how those sound waves affect things, right? So it's only in the case of these things coming together. Well, much like when we square cube features, if we want to see how they work when they're multiplied together, when they're interacted that way, when the two features are interacted that way, we're going to have to do that ourselves. We're going to pass that in as a separate feature. That sort of complexity, the ability to model complexity like that, is something that Other model architectures like neural networks or even non-deep learning networks like even decision trees can handle things like that right in the model. With our simple logistic regression models, just like with our simple linear regression models, we're going to do that ourselves. So we'll pass that in as a feature if we think there's value to those interactions. So we can create composite features. We can add new features. Now, one of the least intuitive things we can do to improve our model performance is remove features. Now, I wouldn't jump and just remove features willy-nilly because we usually probably default to more data is better data. However, we do sometimes see that certain data is just noise, or certain data is correlated because it's correlated with another predictive feature, but in a less useful way. So we may actually not want that. And I actually have an example right here on this next slide. And this can be an example of overtraining, where overtraining, overfitting are catch-all terms for a lot of different ways in which we get ourselves to the point where we perform better on our training data than on the real world or on our test data. And that can happen because we have features that are not really predictive, and we have a model that is sufficiently complex to kind of fake it. So Glenn, let me ask you, if I have these three features that we see here, right? The amount of snow, the number of hikers. Well, actually, there's four features right there. But if we have these features, right, amount of snow, number of hikers, temperature, and number of birds spotted.
Yeah, like
which one seems like it's probably not going to help.
Well, the number of birds spotted is probably the wrong value. I think in the snowfields, in the rest of the planet, those birds are just, the ones that can fly. If they're emus or ostriches like us here in Australia, it might have a factor. But like
those Australian birds, right?
Yeah, like if there's the number of birds spotted and they're just flying overhead, it's probably got zero correlation. Like it might, but the thing is, the model will probably look for some correlation, even if it's really small and tiny. But it's probably, yeah.
Yeah, in fact, number of birds spotted is probably super well correlated to the number of hikers. And number of hikers is correlated to the avalanche because hikers can actually obviously trample the snow and do. So if we're not being considerate, our model is going to notice that correlation, number of birds spotted, and try to predict off it. It's going to see there's a correlation. It's going to predict off of it, but it's not genuinely helpful because we've already got the same data value, the same predictive value is already there and in a better form with number of hikers. So these are what's known as covariant, and they are something we want to avoid, specifically because number of birds spotted isn't actually adding anything, even though we could find a correlation, because it's actually kind of a double hot correlation with that number of hikers. So removing number of birds out of our model is the way to go. It's a little unintuitive, but sometimes removing data is the best thing to do. Since we talked about overtraining, we might as well mention undertraining. And again, undertraining is really just a way of saying that we're not optimizing as well as we could have. For our given model architecture, we could get better performance, right? So we're saying that it might be because we've got too high a learning rate. We're not supplying enough features. We're doing a suboptimal split. So basically, it just means we're not taking as good of an advantage of our chosen model architecture as we could.
And that's something we would work with anyway. We'd be able to pick that up in the measurement of our model when we're testing it against our validation data set.
I mean, especially if we're experimenting with different settings and different ways of handling our data, we'll hopefully see that those things are true.
Right.
Another demo.
Oh, I love it. Excellent. So we're going to look at our third and final exercise, which is really going to look at improving the model again, this time by adding features and also removing features. as well, and getting a sense of what items to remove and what items to add. And then also looking for those composite features we were talking about earlier to see if we can get the accuracy of our model improving. That's the main purpose of what we're doing here. So let's jump over to the browser. I really quite like the fact that we execute all these in Jupyter notebooks. It's such a delight to use. All right, so we're going to do the first thing like we do all the time, which is to load the data set in. And in this case, we'll also split the data set. Again, we'll do that 75-25 split, 75% to the training data and 25% for our validation data. So we'll execute that. It looks like it's executed already, which is wonderful. We've got our data here. So it's the same data that we were working with before. Our training size is 821, test size is 274. Essentially the same data set we had in the previous exercise. And this is that breakdown of the columns I think you were referring to earlier, Jason, where we've got
that glossary.
The thickness essentially, or the frost level of the snow, the thickness, the wind, the number of weak layers, and the number of visitors, and whether it's tracked out or not, essentially. So we're going to do a simple logistic regression, exactly like we did in the first case, but we're doing this as a baseline, really, because we're going to start to improve the model as we go forward. So we've got our logit or logit function where we're inputting just the weak layers at the moment. We'll actually expand this out a little bit later, and we're trying to predict the avalanche. We're working against our training data set, and we want to train the model with this fit call. But the thing that we're doing afterwards is we're actually calculating the accuracy of the model. So as we develop different models, we'll actually pass that into this calculate accuracy function and see how the model's doing. And now obviously we want to get the higher percentage as possible. So we'll use the accuracy method against the avalanche, and then the likelihood that the model has predicted the right value. So we'll execute this one just to get a baseline and see how we're executing. So at the moment, it looks like we're running at 62% accuracy, which is what I think we had in the last exercise as well. But we're going to try and ramp that number up and get it as well as we can. Now, obviously, we could go, let's just add all the features that we have and then see what we end up with the model. And it likely could be that we'd infer the other columns. We saw when we're doing the box and whisker charts in exercise 1 that were particular features that looked like they had a direct correlation with the likelihood of an avalanche. So if we put all those features in, so that's weak layers, the frost level, thickness, wind, no visitors, and tracked out, we'll train that model. This model is called model or feature, and then we'll call that calculate accuracy again. Then we actually get a jump in our accuracy.
So rather nice one indeed.
Yeah, like we went from 61 to 78. I'd say that's a pretty good improvement with just adding a few parameters to that list. That's pretty nice indeed. But if we look at the summary data, we'll execute that. This will be similar to the chart that we saw before. I'll just scroll down so we can see it all. And we've got a few things going on. Jason, do you want to just talk to that for a second?
Well, clearly, we can see our intercepts there, our intercept and all of those coefficients again. And some of them are negative, some of them are positive, so we can imagine the slopes going in the different directions. And we've got that p-value again, right? So I know that we talked about that earlier a little bit, but that is giving us an idea of how correlated that is to our outputs or our dependent variable up on that top left there. So we can see that there is a value right there telling us basically how likely we are to get the all of the output values that we see but in a random world.
But it's not the same kind of correlation that we saw with the coefficient value. It actually means something different. So it's actually the smaller value that you want. And normally there's a threshold value depending actually sometimes on the industry that you're in. So I've studied stats for psychology, and they use anything under 0.05, for example, means that particular feature is more likely to be statistically significant. And I know you're not a fan of that term, statistically significant. How do you describe it?
Yeah, I don't love the term statistically significant because it implies a kind of a magic barrier. And the reality is, if we have what the common barrier is 0.05, which means that essentially there's a 0.05% chance of this happening randomly in a random universe. This correlation could just come up even if there was no causal or properly correlated effect, right? It just randomly co-occurred. So 0.05% chance obviously is a very small percent chance. So 99.5% chance that the correlation had some causative relationship. One thing caused the other, they were caused by the same thing, or some kind of proper causative relationship exists. So obviously that's very good. So I mean, p-value has its place and its strengths. It's just 0.05 isn't a magical barrier is all. So
No.
0.04 is better and 0.06 is worse. And which one you consider the best barrier is just a matter of your domain and how much data you had and what your tolerance for risk is, I guess.
Yeah, that's true. And I know in some of the sciences, like I think in chemistry, they'll use a p-value significantly smaller than the social sciences. But if we look at this, the p-values here, what we can take away from it is that the values that are very small, like the weak layers, the frost level, the wind, and the number of visitors, they're probably the values that we want to keep within our model. And the values that are higher, like the fresh thickness and tracked out, these are probably the columns that we could remove, or the features that we could remove. So we can simplify our model in this particular case, and then just add the columns that we have: weak layers, surface, the frost level, really, the wind, and the number of visitors, and then create that simplified model and then calculate its accuracy. If I go ahead and run that, then I get an accuracy level of 68.1, which is actually just slightly less than I think
78.
78.1. Oh yeah. So we've got that particular value coming through. And
so
we've Go ahead, Jason.
It looks like taking those away had some negative effect, unfortunately, but it was a very small negative effect. So
yeah,
your mileage may vary, I guess.
All right. So we want to look at the all features summary and just look at that data again. And what we can see is that there's a few here that have a negative correlation. So it means is that in this case, as the thickness increases, the avalanches decrease. Likewise with the number of visitors. So we might have that composite relationship that you were talking about before, where we might want to pick that interception and then see how it relates to the two of them. So that's what we're going to do in the next exercise, and we'll show you the way that we can essentially calculate that. If I scroll down here, we've got our new formula, which again, we're trying to predict the avalanche, and we'll apply those layers, like the weak layers, the frost level, and the wind, but this time with the number of visitors and the fresh thickness. This is actually where we're using that composite mechanism. So we're saying the interception, or the combination of the number of visitors and the fresh thickness, has an impact together, and that's what we're looking for. So we'll call this one model with interaction, using that new formula against the training data set, and then we'll calculate its accuracy. So what were we at before? I think we're at 78.1.
And the previous one was like 78.4.
Yeah. So we're hoping to find a better interaction here. And if we look at that, well, we're in the 80s now. So obviously that's a better model. In fact, 83%, that's a pretty good jump on the data set. So 84% accuracy. And if we look at the summary data, we'll actually see where it's got the coefficients and the standard errors and the p-values, that it's mapping the number of visitors and fresh thickness together. And that has a very good p-score as well. It makes you think we want to include that within our model for sure.
Yeah, so that is literally, so you can see that we do still have number of visitors and fresh thickness as independent features. The way that particular model handles that syntax that we gave it, but we also have a new feature. So it passed that in and treated it as a completely additional separate feature, and the data that it passed into it was the product of those two columns.
Yeah,
And
excellent.
that ended up being itself very highly correlated and giving an entirely different kind of result, as we're going to see shortly.
Yeah. All right, so let's actually make some predictions with this, and we'll actually run some of these cells. We're going to look at the model with the interaction, and then look at things like the weak layers in the wind, and then show that as a chart. It might take a few seconds more to execute this, but we can see the model prediction there. So here's the wind levels and then the number of weak layers. It's kind of a little bit tricky to see that chart. So if we rotate it, we can actually see that same S-curve that we saw in the logistical regression too, which is kind of nice.
And you know what's amazing about this is this is a great opportunity to visit a question that we had about an hour ago now.
Yeah.
Which is that S shape strictly a function of having one input variable? And the answer was no, but it's hard to give that good intuition of why. But here we see that we still have, with two input variables here, we're mapping two. We actually did have more than two as to build the model, but looking at it mapped against the two, we can see the S shape now because of some of the other interactions. We also have some wobbliness to it, but we very clearly see the S shape. And we see it, though, only perfectly, or only nearly perfectly, when we look along this angle of weak layers and wind. So that lets us know that we're always going to be able to find a way to get to that S shape. I mean, in fact, there's a very straightforward way, which is you could do the mx plus b along your x-axis, and just treat it as a linear regression, and then your y-axis could be the mx plus b past with the sigmoid, and you always get the perfect S because you're looking at all of your input variables that way. So it's just S-ing what would have otherwise been the slope. But this is actually really strong in its own way, because we can understand wind, we can understand weak layers, and also see that response curve.
Excellent. Cool. So now we can also look at some of the other columns as well. So I'll execute the next one, which this is looking at the number of visitors and the fresh thickness. I don't think we applied the intercept between those before, but if we look at the model prediction, we can see certainly a different shape between that. And if we rotate it, we actually see it behaving very differently indeed.
Yeah, and that's quite a woe. That's quite a woe when we look at that, because we multiplied number of visitors and fresh thickness together and passed that as a third feature in addition to number of visitors and fresh thickness independently. And the complex interaction here created quite the interesting response curve.
Yeah.
Is it possible, Glenn, could you just give us the view kind of looking down where probability is sort of the hidden axis?
Yeah, let's see.
Where we can only see probability based on color.
About there?
Yeah, perfect. So looking at this, the cool thing is we can look at this as just a two-dimensional chart of number of visitors and fresh thickness, and then the color is telling us the likelihood of an avalanche. We can ignore that there's actually a third axis there, although except for the fact that it does have perspective, so it looks a little wobbly. If there were no perspective, this would just be a square with colors. And this would perfectly match if we did a scatter plot where we didn't train a model at all. In fact, I have a way maybe we could do that to show them. But if we had that scatter plot and we look at it with number of visitors and fresh thickness just mapped against each other, how they correlate to each other, and then had color filled in, we would actually see exactly a color filled in for the avalanche, true or false. We'd see essentially this pattern. Now, because avalanche is 1 and 0, not a probability, if we were looking at our input data that way, we would just see yes and no's, or say red and blue, rather than the gradients here, the probability gradients that we see here. But essentially we'd see the same pattern. And it's by doing that during our kind of exploratory data analysis, doing exactly that sort of thing, where we would say to ourselves, gosh, I think maybe this feature and this other feature should be treated together, because I see a pattern that correlates to avalanche, in my scatter plot that isn't easily represented by a linear shape. And you can see, because it's kind of that bow tie shape that you see right there, right? That bow tie shape in the colors. And that's not going to be easily represented by saying fresh thickness goes up or number of visitors goes up and therefore avalanche probability goes up. It's actually a complex interaction.
Cool. Excellent. And we'll just move on. I think that's the end of the exercise there. But we've also got a question in the chat window as well that might be a little bit relevant.
I think it's what I just answered, actually, coincidentally.
You did? Okay. I'll let you speak to that.
Yeah, to clarify, the question was, how could we identify the intersection of certain features if we don't have particular domain knowledge? Which it was actually what I was talking about just as we were getting that question coming in. So that's fantastic. Thanks, Hal.
Awesome. All right. Well, let's go back to the slide deck then, Jason.
Absolutely. All right, and it's time to go into a knowledge check.
Oh, wonderful. Cool. So if you're following along, you can go to https://aka.ms/learnlivetv and answer in the chat window. I think there was some technical issues with Learn TV before. So if you can't,
looks like Learn TV is operational now. So people,
excellent.
Hopefully there's some folks watching on Learn TV in addition to our other platforms. So
awesome.
if you want to participate on the actual interactive version of our Q&A, go over to Learn TV instead of watching on the other platforms.
Awesome. All right, so let's start with the first question. So what is the difference between classical regression and classification models? Is it A, regression models provide labels such as cherry, banana, but classification models calculate continuous numbers? Is it B, classification models and linear regression or linear regression models are two names for the same things? Or is it C, classification models provide labels such as cherry and banana, but regression models calculate continuous numbers? What do you think, Jason?
All right, let's see. Regression models starting today. Regression models provide labels such as cherry, banana, but classification models calculate continuous numbers. Well, that's not right. Classification models and linear regression models are two names for the same thing. I'm apparently having a hard time reading these questions for some reason, but that's also not right. Finally, classification models provide labels such as cherry, banana, but regression models calculate continuous numbers, and that is in fact the right answer.
Cool. Yay. Let's say that. And you know what? We've just got really awesome people on the line today because everyone that answered that got that correct.
Bravo, folks.
We can't.
Len and I will take some credit for y'all getting it correct. I'm just saying.
Yeah. All right, moving on to question 2. Question 2, how can we improve real-world model performance? By adding features, B, or both adding and removing features can be useful depending on the situation, or by removing features.
Well, let's take the independent options first. So is it A, adding features? Yeah, that can help. C, removing features. Less common and somewhat unintuitive, but yeah, that can help. Okay, so I guess that means B, both adding and removing features can be useful depending on the situation. Yes, indeed.
Awesome.
The answer is B.
Answer is B. Excellent. And you know what? Everyone that, again, has answered that 100% correct. So
crushed it.
That's awesome. Let's see if we can get 3 for 3 today. Otherwise, Jason and I are going to go back and build a machine learning model on how the predicted correct answers are coming in for these exercises. That'll be good. All right, question 3. What is one reason why logistic regression uses log loss rather than a more intuitive cost function? Is it A, log loss punishes very wrong probability predictions more harshly? B, it is the only way to calculate error for categorical labels? Or C, log loss is more permissive to model error if that error is close to correct?
All right, so let's flip this one. Let's kind of go this time and say, all right, log loss is more permissive to model error if that error is close to correct. Is it more permissive to model error if that error is close to correct? That's actually not entirely crazily wrong, but it's not a helpful answer, I think. So, maybe that one's kind of sort of a little bit not crazy, but let's keep going. It is the only way to calculate error for categorical labels. Well, that's very wrong. All right, so how about a log loss punishes very wrong probability predictions more harshly? That is more correct, but man, I somehow missed this before, and I'm just going to be real honest with everybody right here on live TV. I think both A and C have some validity. So we're going to go ahead, and once again, I'm looking over at the answers. We're going to go ahead and call this 100% correct again. That's what I said. What do you say, Glenn?
Well, I like the positivity as well, and you're right. But everyone's answered A and C. I think we've got, what, 3/4 of people have answered A, and the 25% remaining have answered C. But yeah, let's go an all-round victory for today.
Everyone wins.
Yeah, excellent. Cool. So let's move on to the summary for today, because we're at the end of the session. It's been a fun ride. How would we summarize what we've covered today, Jason?
Well, the main thing we've done is really drilled into our logistic regression function, which is our binary classification model. It's not the only way to do binary classification, but it is a really nice next step when we've been talking about linear regression. So we've talked about classification principles in general, and we've talked about the logistic regression in specific, how the loss function ends up needing to be different. And we've talked a little bit more about kind of data prep and data health and how we can improve our models. And some of those principles apply to everything, whether it's linear regression or logistic regression or binary trees. Some of those principles are just good general principles.
Awesome. Now, we do have something that's very exciting. We're actually 2/3 now officially through our entire learning path, which is 9 modules in total. So we've got 3 more to go, which is wonderful. We're going to look at architectures and hyperparameters in next week's session. We're going to look at confusion matrices and data imbalances after that. And then we're looking at optimizing model performance with ROC and AUC, area under the curve. And we'll go on from there. But I'm mindful of the fact we've only got a few minutes left, Jason, so we might have to just remind everyone where they can go to get access to this if they're following along.
I think we did a lot of questions today, so we're gonna have to bounce through that Q&A slide, I think, and just let everyone know that they can go back to aka.ms/learnml-classification in order to go through this module yourself. Again, execute all the code, change the code, do whatever you want. And if you just drop that -classification there, in other words, you go to aka.ms/learnml, then you're going to get the entire learning path. And actually, all of these episodes go through the option 2 learning path, but option 1 and option 3 have even more fun modules that you can complete that are all about machine learning.
Excellent. Cool. Well, that brings us to the very end of today's session. Thanks, Jason, for coming along this fun ride with me. Thanks to our producer, Rob, and to our moderator team. And we'll hope to see you next week. Bye for now.